Great. Okay. It's a distinct pleasure to give the first talk here at MikeFest. It was very hard to decide what to talk about. You just heard from Costas' summary. Mike's interests have been diverse to an extreme. He's accomplished in many areas, and I'm not accomplished in most of them. But I decided maybe to do the safest thing, talk about a number of things I've been interested in, and because of his broad interests, at some point or the other, they all intersect in a significant way with Mike's interests. So I'll do that. I'll say a little bit about a few subjects. I'll run out of time, unfortunately, before I get to the last subject I had planned to talk about, which is some work in computational biology. But we'll get where we get. So let me start a little bit with why I'm here. Why would I be talking at MikeFest? Well, there are different versions of the story. Mike was one of the first and most imposing talks I heard when I was a graduate student at Princeton in the early 90s. He had moved to Rutgers with this incredible group. And I encountered him when he came to IAS to give a talk about conformal field theory techniques for large N group theory. This is a good 5 years before everybody started working on large N conformal field theory because of ADS-CFT. What I got out of this talk at that young age was that I needed to learn a lot more about conformal field theory, large N, and group theory to survive in the field. So it gave me a good prescription for things to learn about. But I'd later come to know, even as I grew older and thought I knew more, that you can always count on Mike's work to suggest a steep new learning curve in all kinds of fields, regardless of how old and advanced you consider yourself to be. This has ranged over the years, in my case, from fields like random geometry, which became relevant later, to topics like artificial intelligence, where he is moving now. And it's been a continued inspiration to learn from his trajectory. There are a number of much more personal encounters I had with Mike. One is I was one of the people who moved to Rutgers in 1996. There was an incredible affirmative activity there. Matrix theory and D-branes and string duality were all in the air. Much to my surprise, it was actually kind of hard to get a good apartment in central New Jersey. But Mike said, "Oh, I heard you're coming this summer. You need a place to stay. Take my apartment." I'm not sure where he was. Maybe he was in France. But so my relationship with Mike started with this unexpected kindness. He actually gave me his apartment for a month in July of 1996. Much later, we talked a few times over the years, but much later in the mid-2000s, we collaborated both literally but also more spiritually in the sense of building a community on studies of something called flux vacua, which are compactifications of string theory with certain background fields, so they're not vacuum solutions. Those works and that era and what came out of that era in Mike's work significantly, also in work of cosmologists and others, has really greatly shaped my view of fundamental physics. It's shaped it in a way that lasts to this day, and I'm pretty convinced that some robust features of what we found then are going to survive as part of our picture of the string theory landscape. Now more generally, and this will be more relevant to my talk today, his work on many aspects of quantum field theory, of D-branes, of geometry, have all served as an inspiration in very concrete terms. And we'll see that in my first topic. OK, so my first topic is actually going to be very, very specialized. It's metrics on a particular kind of manifold. So string theories live, as you all probably know, in some natural sense in higher dimensions. I think 10 is a favorite number. Since we don't, it's been natural to find ways to lower the number of dimensions by saying that some of them are living on a compact space too small for us to see. Most of the time, as a sociological statement, string theorists do this while preserving some supersymmetry. There are different reasons for that. Early on, it was because of the motivation to connect to phenomenology, which was thought to promisingly host supersymmetry at the weak scale to explain the Higgs mass. More recently, that motivation could be called into question. We don't know whether there will be supersymmetry at any reasonably low energy. But there's a second practical reason we preserve supersymmetry. It gives us a degree of theoretical control over a very complicated theory and allows us to make statements that are precise. So it's a first place to look in the normal sense of physics, where you look at the simplest objects first. So a standard class of choices that preserve supersymmetry are these spaces conjectured to exist by Calabi and proved to exist by Yau. The statement is that if X is a complex Kähler manifold with vanishing first Chern class, then it admits a Ricci flat metric for each choice of the cohomology class of the Kähler form. Some of the conditions in the first line allow for the existence of supersymmetry, so that spaces have reduced holonomy and so preserve killing spinners. And the Ricci flatness is important because, as a theory of gravity, string theory in some leading approximation leads to the Einstein equations. And so a vacuum solution should be Ricci flat. OK, so Yau proved this. The theorem sounds sort of fancy, but because the hard condition there is a topological condition on first Chern class, it's easy to write down examples in some crude approximation. You just use a junction in algebraic geometry. So if you take the right kind of polynomials in projective spaces, you get examples, in some sense, of Calabi-Yaus, things that should admit such a metric. Here's an example, not irrelevant to my talk. You work in CP3, so there are 4 homogeneous coordinates, and you write down a quartic. I chose a pretty simple quartic there. And the statement is that should be one of these spaces proved to exist by Yau. And in this case, it's an example of something called a K3 surface. Now, Yau's proof is a beautiful achievement, but it's non-constructive. Now, on the other hand, for various purposes, maybe one of which will come up here, it might be nice to actually know the Ricci flat metrics. Now, you could mean this in 2 different senses. One is as a practical matter. You might want to be able to write an explicit approximation to an accuracy good enough to do some kind of explicit construction. And Mike has written a series of superb papers. I think also Donaldson and Hedrick have written related works discussing aspects of this problem, usually from the viewpoint of what I would call practical numerical methods, though they involve some pretty high-powered math. And I think they can do a pretty good job now of, at least in certain neighborhoods, getting approximations to the metric. And I don't see any obstruction to that being refined further and further and further. Here I'm going to discuss something else, which is an analytical approach. And the goal isn't so much to get a formula for the metric, though there will be formulas, not so much in my talk, but they come out of the approach, but more for conceptual reasons that you'll see. It gives some, it relates the metric to series of integers. And so somehow an integer packaging of the form of a Calabi-Yau metric is an aesthetically pleasing thing to have. Sorry? It's out there. OK. So the K3 surface that I started with provides a nice Goldilocks case for a program to write down metrics. It's appeared in central ways in string duality, so it's a natural object of study. But also it's simple. It's somehow the lowest dimensional compact non-trivial Calabi-Yau. There are tori. They're a little too easy. So it's a place to start. If you can do this, it's not clear you can do harder things, but you do the first thing you can do. So can we find Ricci flat metrics on K3? And anything new I say here, there will be a lot of review of technology, and I'm going to try to stay qualitative. It's early in the morning, and especially for me, since I'm from California. But anything I say that's new was based on work with these 2 young men, Arnav Tripathi and Max Zemet, a mathematician and a physicist who's slowly becoming a mathematician. So mirror symmetry is often used by string theorists to solve for the geometry of the moduli space of Calabi-Yau manifolds. And I think my slogan is that here we're going to do something slightly different. We're going to use mirror symmetry to solve for the metric itself, okay, the metric on the space. So what do I mean by this? Well, mirror symmetry isn't just a symmetry of the 2-dimensional sigma models with Calabi-Yau target. It was generalized in the mid-90s to also relative dualities between supersymmetric quantum field theories. And in particular, 3-dimensional quantum field theories with 8 supercharges, usually called n equals 4, at least in the counting prevalent in America, are a relevant setting for mirror symmetry. So let me explain what it means there. 3D n equals 4 supersymmetric gauge theories have 2 kinds of multiplets of fields at low energy, light multiplets. They're vector multiplets. Let's see if, yeah. Vector multiplets, which have, unsurprisingly, a gauge field, a vector field, a scalar partner, and the adjoint representation of any gauge group G, and fermions. And again, in keeping with culture at Stanford, I neglect the fermions. And then there's the hypermultiplet, a matter multiplet, which has a chiral charged field under the gauge actions and some representation R. It's conjugated in a representation R bar, and then a bunch of fermions. And since there are scalars both in the vector multiplet and in the hypermultiplet, there can be different branches in the space of vacua, the moduli space of vacua. You can give expectation values to these fields and get what's typically called a Coulomb branch. Coulomb because since these are adjoint, abelian factors in the gauge group remain massless along the Coulomb branch. You can also give, if they're sufficient in number, expectation values to the quarks in the hypermultiplets, giving something called a Higgs branch for the predictable reason. The gauge field gets Higgsed by the charges. And then there could also be mixed branches, which are not going to be really relevant here. But if there's enough matter, there could be branches where you're sort of in a hybrid. Importantly, with this much supersymmetry, 3 dimensions and n equals 4, both of these moduli spaces of vacua are hyperkähler manifolds. So there's a hyperkähler Higgs branch, there's a hyperkähler Coulomb branch, and there may be mixed branches. Now, in the context of such supersymmetric gauge theories, we normally can't write down the exact infrared theory. We write down a massive description. There's a group and some matter, and we try to guess what will happen when we flow to the infrared. And it was realized, as I said, in the mid-90s, that there can be relatively robust and generic situations where, given such a massive theory A, there will be another theory B with the remarkable property that the Coulomb branch of A is the same as the Higgs branch of B. These are both computable, even just given the massive description. And the Coulomb branch of B will be the same as the Higgs branch of A. And if you think about this, there's in some sense a simple analogy to the typical facts about mirror symmetry on moduli spaces of Calabi-Yau manifolds. But this is anyhow a reflection in dynamics of gauge theory. I'll actually be interested in generalizing this to something a little more general than field theory. I'm going to elide the distinction. Again, it's early and it won't matter too much. So let me do a warm-up example for the relevant theory A, the theory whose Coulomb branch I'll be studying. String theory has various branes. One of the simplest, one of the first known, was the Neveu-Schwarz 5 brane. This is a 6-dimensional theory. We can compactify it on a 2 torus to get a 4-dimensional theory. So there's the 2 torus. And then the relevant low-energy gauge theory, it turns out. The NS brane has a tensor field on its world volume that's hard to think about. But once you compactify, you get a U1 gauge theory. And the Coulomb branch moduli space of vacua of that theory is just the T-dual torus. Now, if you compactify on an additional circle to get to 3 dimensions, which is my setting, instead of just a complex Coulomb branch, you get a hyperkähler Coulomb branch. You get 2 more scalars. There's a Wilson line from the abelian gauge field, which can take a Wilson line on the circle. And then there's a 3D photon that remains. And just algebraically in 3 dimensions, you can sort of do this. So you get another scalar. From, for instance, the M-theory picture of the same configuration, it's clear that the moduli space you get just becomes a 4 torus. Okay, so we have a 3-dimensional theory whose Coulomb branch is a 4-dimensional torus. Now, I warmed up with this because I'm going to be interested in a slightly more elaborate theory A, whose moduli space is a K3 instead of a 4 torus. And I wanted to make sure that the basic idea that a compact Coulomb branch whose target is Calabi-Yau can emerge doesn't seem surprising. The simplest case is that of the NS5 brane. So now we just run the same story. We do it, however, in heterotic string theory, or in terms of the D5 branes of the type 1 theory. There are different descriptions of this theory in 6 dimensions. They're not all equivalent. But I'll start with one. Once you add a circle, they all become more or less equivalent. One description of this theory is as an SU2 gauge theory in 5+1 dimensions with 16 doublet hypermultiplets and an SO32 global symmetry. That SO32 is very much the same as the SO32 you all know from anomaly cancellation. So then we run the same story. We compactify first on a 2 torus to get to 4 dimensions. It is at low energies a rank 1 one-dimensional Coulomb branch, supersymmetric field theory. And in fact, the geometry of the Coulomb branch is now a sphere. There are different ways to see this. Maybe the easiest, and the one that I'll use, and that's actually quite relevant to Mike's work, is that the heterotic string on a 2 torus is dual to something called F theory on an elliptic K3. This is a relative of a duality relating heterotic strings to type 2 strings. In the F theory picture, there are D3 branes. And this wrapped 5 brane becomes a D3 brane moving around on the base of an elliptically fibered K3 surface. In that description, it's obvious an elliptically fibered K3 typically has degenerate fibers of the elliptic fiber, usually 24 if the K3 is smooth. And so there are 24 interesting points in this moduli space. This means that on the Coulomb branch, in addition to points where there's just a photon, there are 24 points where something interesting happens. And up to duality, what the interesting thing that happens isn't that surprising. The F-theory description of these points is as, in some duality, frame D7 branes. And so what happens is you get a white BPS electron. Now, if you compactify this on an additional circle, the elliptic fiber becomes geometrized, just as it did with the type 2 NS5 brane. And so the moduli space, and I guess I dropped an I there, becomes the K3 surface itself, not just the sphere base of the vibration. The elliptic fiber comes from the Wilson line of the gauge field on the circle and from the dual photon. So if we can run some playbook to find the metric on the Coulomb branch in this three-dimensional gauge theory, then that same playbook will give us an approach to finding metrics on K3 surfaces. Now, here's the way I like to think about this, and this really goes back to a very beautiful and extremely short paper that Mike wrote in 1996. In fact, I remember this paper because the abstract started with some sentence like, last week Sen said ... And so that told me, again, I always learned from Mike's papers, one of the things this told me is you can't take a break in string theory because important developments can happen last week. But anyway, I think they could have come pretty close to yesterday. Maybe there was a weekend in between. So what they found, oops, sorry. Mike and Tom Banks and Adi Seiberg found that if you think of the D3 brane probe in terms of its world volume field theory on the K3, then it's very analogous to Seiberg-Witten theory. In certain limits, it becomes, in fact, literally a Seiberg-Witten theory with massless quarks when the 3 brane approaches 7 branes. And as I said, for a generic smooth K3, the points where the elliptic fiber degenerates give light electrons. So mathematically, there's a rich story of these sort of n equals 2 gauge theories in 4 dimensions and n equals 4 in 3 dimensions, which involves something called a Seiberg-Witten curve. So what is that? It says that over the moduli space in 4 dimensions, over the Coulomb branch of the 4-dimensional theory, there is an elliptic curve and a preferred meromorphic differential on that curve that can be used to determine the geometry of the Coulomb branch. So this differential we'll call lambda. The elliptic fiber has these A and B cycles. And roughly, the special coordinate coordinatizing the Coulomb branch is given by 1 period of lambda on the torus, and an important holomorphic function called the prepotential, which governs the geometry of the moduli space, is given by the other period. And then, for instance, in low-energy physics, the gauge coupling constant, and with this much supersymmetry also the metric on moduli space, is given by the second derivative of f. So the important point is there's a geometric object, and if we can compute periods of the right differential on this geometric object, we get the prepotential, and that determines the metric. Okay, and in terms of the prepotential, the explicit formula for the metric is given there. Importantly, and this will come up as we go along, all particle states in this theory satisfy a supersymmetric BPS bound for Bogomolny, Prasad, and Sommerfeld. It says that the mass of a state with charges in this theory with a one-dimensional Coulomb branch, QE and QM under the abelian gauge field, satisfy a bound, that the mass is greater than some function z of the point on the Coulomb branch A, QE and QM. And this z, in turn, is governed by the one object we've talked about, f. So if you know f, you also know a precise bound on masses of particles. And the lightest particles at a given point that saturate this bound are somehow protected. They're supersymmetric, they're in short multiplets of the supersymmetry, and so they're exactly stable. Okay, in terms of these ingredients, which are ingredients of the 4-dimensional Seiberg-Witten theory, but are somehow familiar, it's easy to give a cartoon picture of the 3D Coulomb branch geometry too. So I'll start by doing that. So this 4D theory has an action. For the photon, it looks like, well, there's an f squared, and there's a theta angle multiplying ff dual. And so at a given point in moduli space, we can sort of associate this data with a tau, which is given by the theta angle on 1 over g squared, 1 over e squared, which gives us some kind of auxiliary torus, with tau being its complex structure. So when we reduce to 3 dimensions, this torus becomes physical. That was the story I told you before. The action for the scalar field spanning the torus is then given in this way, where dB comes from a Wilson line and sigma comes from vice versa. dB comes from a dual photon and sigma from a Wilson line of the gauge field on the circle. And if you look at the metric, the kinetic terms in this action, that gives an elliptic curve over the old Coulomb branch in 4 dimensions with an area controlled by 1 over r, the radius of the circle. So the leading large R metric, the semi-classical metric, is given by combining kinetic terms for the new scalars here with those of the old 4D Coulomb branch fields, which we learned how to compute from Seiberg and Witten. Now, that's an old and classical result. There are 3 important sources of corrections, and without knowing how to compute those, we're not going to say anything very interesting. There are one-loop corrections in 4 dimensions. There are corrections from instantons in 4 dimensions, summed by Seiberg and Witten. And then there are new sources of corrections, which come from instantons in 3 dimensions. And roughly, we can think of these as for every BPS particle you had in 4 dimensions, when you reduce, it can run around on the circle, viewing the circle as Euclidean time, and give you new instanton corrections in 3 dimensions. Now, it's not only early in the morning, but I also have finite time. There's a very comprehensive series of papers by Gayato-Bornitsky that have developed a beautiful formalism for how you compute Coulomb branch metrics of 3D n equals 4 field theories, given this general setup and the need for this data. And I'm just going to extract little bits of it to give you an overview. Okay, so their basic point is that if you can compute indices that are given in terms of certain massive probe particles, so what is this index? You insert by hand a massive probe particle of charge gamma, some electric and magnetic charge. You compute in the Hilbert space consisting of this thing and any other external charges from the theory, a trace. It's a supersymmetric index, so there's a trace -1 to the f. You weight everything by the action of a Hamiltonian governing motion around the Euclidean time circle. And there's an insertion of a Wilson line of any charge q that happens to be in this trace as you trace over the Hilbert space of things in the presence of the external charge gamma. This is an odd external trace. We'll dispense with it in a minute, but it's an intermediate object that's useful for them to define. U coordinatizes the point on the Coulomb branch, theta the Wilson line. And what's this thing here, zeta? Well, zeta parametrizes a choice of complex structure on the Coulomb branch, which is hyperkähler. So the way you can think of it is in defining trace -1 to the f, I'm trying to define a supersymmetric index. With so many supercharges, I have to decide which supersymmetry I'm taking an index of. And zeta parametrizes the inequivalent choices of supersymmetries. Okay, so it's just something telling me in which subspace of superspace I'm taking this trace. I'm not going to go more into the formalism here. It will suffice to say that if we can compute these indices for a basis of the charge lattice, that is, in this case, for roughly 2 charges gamma, then we can determine the full suite of 2 forms, the Kähler form and its partners, that characterize a hyperkähler manifold, which has a triplet of 2 forms. And there's an explicit formula. You can get the 2 forms by computing log of the x gammas for a basis of the x gammas. So what data do we need to know to compute these indices? And that I'll now try to tell you, and it becomes slightly more intuitive. Well, first consider the large radius limit where any formula should simplify, because when the circle is large, instantons going around the circle are highly suppressed. Okay, so we'd like to compute this trace. It's come out a little hazy here. I had to compress the file to send it to IHES. Okay, but it's the same trace I had on the previous page. And at large radius, semi-classical reasoning teaches us that basically this Hamiltonian is given by the central charge of the theory. It's a supersymmetric index. Only BPS states contribute. And the BPS Hamiltonian, the energy of a BPS state, is governed by, well, it propagates a distance r, and it's governed by the central charge z gamma. And the combination here with phases is because of the subtlety that there are many possible choices of supercharge, and I have to choose the right zeta to get the right supercharge. Okay, but this is basically just the BPS formula. Now, for the precise case at hand of this F theory on P1, the 4D Coulomb branch geometry, gives us something that was already known. It was known, for instance, to Green, Shapir, Vafa, and Yau in 1990, called the semi-flat metric. I won't go through the details, but there are 24 points with light electrons. And you find a simple formula where here tau is the complex structure of the torus varying over the U-plane. There are 24 points where there are light electrons. These are the UAs in this formula. And the metric looks something like this. Interestingly, the way they derive this is by using facts about 7-brane solutions, though in 1990 they weren't called 7-brane solutions. And there's an interesting appearance of the eta function here, which just manifests the periodicity in tau. So here, U is heuristically the coordinate on the 40 Coulomb branch. Z is the coordinate on the elliptic fiber. Yeah?
How do you get 24 branches out of 16 Calabi-Yau?
Once you compact, you mean why do you get 24 singularities? It's because in
3, yes, I know, but can you package this information in gauge theory, in the super gauge theory?
I mean, this is going to be related to the splitting of the origin in the case where you have coincident 7-branes, right? So already in pure Seiberg-Witten theory, you sort of get a multiplicity of points from splitting of one origin.
So there you have one coupling and four quark masses. So that determines this condition of 6.
Oh, no, I see. So the 24 parameters aren't all independent.
They're not.
No. So the 24 parameters, there's an 18-dimensional family of these points, and the 24 parameters move around in this 18-dimensional family.
So you have 16 masses and what coupling?
Presumably Wilson lines of some sort of background fields. But yeah, this is just a statement that elliptic K3 has 18 moduli. Does that answer your question? Okay. Right, so here U was a coordinate on the Coulomb branch, Z the coordinate on the elliptic fiber, and this is a known formula. So it's not so satisfying. This was known in 1990. To get a more complete and satisfying answer, you need to include more extra instantons that arise in going from 4 to 3 dimensions. Now, in this duality frame, we can actually state answers in terms of BPS particle numbers, and that will become more intuitive. And that's good because these are morally more topological information than a metric. We could debate how much easier they are actually to compute, but morally you feel better packaging the information in a set of integers than directly in the metric. Heuristically, we expect the following. If we say that these chi gammas defined by Guyot-Morenitsky, GMN, take a semi-flat form plus corrections, well, the corrections will be of the form e to the minus r. They'll come from these instantons. Okay? And in fact, you can prove that these x's, and this was the burden of the work of GMN, satisfy an integral equation that determines these corrections order by order in e to the minus r. And this integral equation basically has only one input, which is the BPS spectrum at the point U on the Coulomb branch you're interested in every charge sector. So given omega, the degeneracy of BPS states in a given charge sector at a given point on the Coulomb branch, starting from the semi-flat limit, there's an integral equation you can satisfy to determine order by order better and better approximations to the metric. Okay? And this integral equation can be solved iteratively if you're given the BPS counts. So, again, you can do slightly better than semi-flat in a way very analogous to what mathematicians Gross and Wilson did, again, many years ago, by just working on a smooth K3 and including the simplest instantons that arise in 3 dimensions just due to the BPS electrons at each of the 24 electron points. So add those going around the circle. Those are the electrons that ever become light. And that actually gives you a pretty good approximation named after those folks. But again, we'd like to do better. So how do we determine the BPS invariance more generally? And OK, so here string duality answers the question. Okay? It provides a dual frame precisely in the spirit of mirror symmetry I talked about before, where the metric computation becomes purely classical. And just as in old mirror symmetry, the integer data can in principle be read off to package the answer more elegantly if you wish. So how do we see that? Well, this is a 60th birthday. So I feel comfortable saying things that are known to old people. So old people who are alive in the 1990s know these old-fashioned statements, like the heterotic string on T3 is the same as M theory on K3. The wrapped NS5 brane on a 3 torus is the same as a transverse M2. Okay, and there's a whole list of such lore where these symbols are only known to those of us who are old enough. The brane theories, it turns out, are related by an analog of 3D mirror symmetry. This was shown sort of in various local approximations by Gukov and Kapustin, but it's true more exactly in a sense I'll tell you now. So the point is we can take the M theory side, which has a 2-brane whose action isn't very well known, and reduce it on a transverse circle to give ourselves a D2 brane of type 2a string theory. And the nice thing here is that's the B side of the mirror pair. We're interested in the Higgs branch metric. And it turns out Higgs branches aren't affected by this process of compactification. So by non-renormalization theorems, the classical Higgs branch metric on our B side for the D2 brane probe will give us the desired formula for K3, just at the classical metric. Now, viewed through a suitable mirror map that we've implemented to some extent, it will also encode an infinite number of BPS state counts. That leaves us with a classical problem, but it's not always true classical problems are easier. So how do we obtain a tractable formulation of the D2 theory on K3? Here again, maybe I haven't emphasized it enough in the first part, but again, we rely very heavily on Mike's work. So Mike and Greg Moore wrote a paper which, if you can translate the very heavy technology that was necessary, tells us how to figure out what D-brane gauge theories on orbifolds do. Okay, so one of the easiest things you can do with K3 is make a Kummer surface, for instance, make a K3 that's T4 mod Z2. Take a D2 probing that orbifold. There are some interesting fixed points, where the Z2 action degenerates. And we can take sort of their formalism and try to use it. Okay, so we have a very explicit expression from Mike's work for the gauge theory on such probes, including the blow-up modes that make a smooth K3. That's crucial, or you're not doing anything. For things like the Z2 fixed points on a toroidal orbifold. Okay, now at this point, a detailed talk on the subject would have to go through many more steps just to understand the classical side. Let me tell you what they are for logical completeness. We'd have to discuss a local construction near, for instance, each fixed point of a Kummer surface. As I said, that's Mike. We'd have to promote it to a global construction because we're not interested in describing the metric here on an ALE space or an ALF space or an ALG space. We're interested in the full metric. And for that, we have to promote this to a global construction that knows that the K3 is compact. And precisely because of the excitement over matrix theory in the mid-1990s, Waddy Taylor, who will speak later this week, introduced a very simple and elegant formalism to take these orbifold theories and promote them to global constructions by somehow going to an infinite dimensional gauge group. Okay, and I won't do that here. It's in our papers and it's in other talks. And then you have to show that when you introduce the resolution parameters, the phi Eliopoulos terms or their duals in the gauge theory that blow these things up, and when you integrate out the massive fields in the D-brane theory so obtained, what remains are the light fields. They have kinetic terms. Their kinetic terms contain an approximate formula for the K3 metric. Approximate in the sense that you can iterate this integral, you can integrate out the tower more and more accurately, and read off a better and better analytical approximation. Okay? So I'm not going to do any of this here. I've discussed it in other talks, and it can be found in publications. I can provide a summary of the checks that were provided. We checked at lowest non-trivial order in blow-up mode expansions that far from the corners, the metric is Ricci flat. That's in this unpleasant and long paper. We checked that a suitable Poisson resummation of the classical formulas yields a match to a Coulomb branch picture and lets you read off the BPS spectrum of simple limits like SU2 gauge theory with some number of flavors. Okay, that's also in that unpleasant paper. Tripathi and Zimmet, who are much stronger than me and have much more strength to bear the unpleasant, used this formalism to reproduce and predict new BPS counts in certain limits of certain field theories. And currently, they and a mathematician at Stanford, Andras Vassi, who's a relatively well-known analyst, are putting the perturbation theory, just defining the classical side, on a firm footing in analysis. Okay, it turns out that's a math thing. And again, I don't know whether it's above my pay grade or orthogonal to my pay grade. I'm not doing it. They say they're making good progress. But this is a case of mirror symmetry where the classical side needs to be analytically well-defined. And that's what they're doing. OK, so that concludes the first part of my talk. I think the main point there was to showcase the power of some of Mike's work on D-branes. And one lesson there is, he had relatively simple and foundational observations. Okay, some of these observations about branes on orbifolds, about branes probing geometry, they're among his simplest papers, the ones that I can understand. But nevertheless, they, if you use them appropriately, I think they'll lead to progress going forward.
So how many parameters do you have in the end?
In the end, you actually have enough FI terms to blow up everything. So in terms of counting, you have 58 parameters in the metric, which is the correct number for the space of metrics on K3. In string theory, you have 80 because of the B field, but you have all 58 parameters. Whether you can prove convergence, and extend the convergence analytically is another set of questions.
And how far this goes beyond what was known like 20 years ago from model space of instantons and photons?
So I think for K3, this is the first example of a system where we claim we can read off all disk counts. So there's a reformulation of this problem in terms of counting disk instantons on K3. My claim would be that if you work in the classical...
Just the metric on K3. So yeah, you can read it off from doing the differential geometric calculation.
Correct.
So you're doing something else, right? You're relating to some counting problem.
That's correct. Yeah. But sorry, for the metric itself, I think also the classical slide provides the first analytic approach that I know of.
Okay,
we can discuss it. Yeah. Okay, I'm going to morph to another topic. And again, my goal will be to present a big picture of some developments that I personally consider interesting. Again, to the extent that I say anything new, the hero of the story will be the D-brane. And again, there will be a common thread to topic 1 and some very simple aspects of work of Mike's. So here's a picture that we all know and love from our youth. This is where we normalize trajectory in a space of couplings. There's a critical surface. Maybe there's a fixed point. This is supposed to be a depiction of a space of couplings in a quantum field theory under RG flow. And in thinking about quantum field theory, I think it's fair to say high energy theorists have grown up with this picture and the paradigm of Kadanoff, Fisher, Wilson, and many others firmly in mind. Now, whether because of their starring role on the string world sheet, their role in holography, or just their role in defining QFT in the ultraviolet, I think it's fair to say conformal field theories have often been our objects of interest. Certainly, ADS-CFT alone has generated 20,000 papers in the last decade. Now, one of the most interesting developments in the past couple of decades from my perspective has been the increasingly central role played in condensed matter physics, not by conformal field theories, but by gapped but nevertheless highly non-trivial phases of matter. Okay, and the tools and questions of interest here, I don't have anything precise to say, but they feel rather different. They suggest different problems and different techniques. Okay, and again, sorry for the data compression. This is a picture of electrons in a plane that you could get, for instance, by trapping them in a semiconductor heterojunction. And in the presence of a transverse B field, they move in Landau levels, okay, in these circular orbits that characterize the Landau level. This is supposed to be a picture of plateaus in the Hall conductance as a function of magnetic field or filling fraction. And starting with the discovery of the quantized Hall effect, and then the fractional quantized Hall effect, it was unearthed that topological field theories, such as Chern-Simons theory shown here, are crucial not just conceptually, but for their role in nature. Okay, so here's the simplest poster child of a topological field theory. There is no metric in writing down this Lagrangian. A, in the simplest case, is a U1 connection. More generally, there could be a group G, and you add this cubic term. K is a quantized level. To quantize it correctly, there should probably be some pi's here, which I neglected. And the important point about this theory is that considered on a space X, physics is independent of, in this case, most of the details of the space where the theory lives. It's topological. And a common feature is that the ground state degeneracy here is both non-trivial, although there's no evident symmetry breaking. There's a higher form symmetry breaking, but no evident symmetry breaking. And this ground state degeneracy is in fact determined topologically by the topology of X. So for instance, the abelian Chern-Simons theory at level K on a genus G-Riemann surface has a large ground state degeneracy given by K to the G. And this can be understood in terms of higher form symmetries if you want to, but is certainly unconventional from the old-fashioned viewpoint. Now, I should say for string theorists, there are other examples that we often call topological that depend on more structure. For instance, the A and B sigma models that are certainly interesting depend on some finite dimensional subset of metric data. So they're not strictly topological, but since in every natural sense the space of metrics is really big, they get called topological anyway. They depend on a small subset of data. Here's a second example of such an interesting phenomenon. More from theory now than experiment, but there's a rigorous theoretical example due to John Embry. This is the many-body localized phase. So they're, roughly speaking, quantum systems where local thermalization does not occur. Okay, and related to that, they can exhibit non-ergodic dynamics. So in a normal quantum system, what you'd expect is if you fix all conserved charges, then the sort of phase space of states with typical average properties, including that fixed average charge, is explored sort of completely by dynamics of the system. Yeah, Vijay?
Could you say what local thermalization precisely means here?
No. What I'll say is that there are some hypotheses under which ETH applies, and where this eigenstate thermalization hypothesis applies. What it means is some kinds of correlation functions obey properties that make them roughly asymptotic to correlation functions in a thermal field theory. We could be much more precise about that. I'm not going to try to be here. I understand that this is one of the homes of such thinking. Is that a satisfactory answer to your question or not?
Semi. What's the difference between local and global thermalization?
Yeah, I'm happy for this purpose to replace it with global. Okay? Good. Okay. Relatedly, so these systems that I'm interested in violate the eigenstate thermalization hypothesis, and they can exhibit non-ergodic dynamics. They don't explore the full phase space at fixed charges when you dump some energy into them. So it's theoretically interesting to ask which systems can break ergodicity. I should say that's not really necessarily the reason the condensed matter theorists who care about it. It's also spiritually related to an urgent question, which is the set of questions involved in constructing modern quantum devices, wherein, in some real sense, the central question is how do you localize excitations or localize bits of information in such a way that they don't explore phase space, that the information remains sort of unentangled from the rest of the system and is preserved for all eternity. Okay, and it's that, I think, underlying technological driver that's really explained the great interest in these systems. Okay. So my topic is now going to be a sort of third recent example of a new kind of phase of matter, which is the fracton. And I don't know how much time I have exactly, Costas. I have like 15 minutes.
10 minutes.
10 minutes, OK. I'll speak fast. So what is the theory of fractons? Well, there are two reviews by condensed matter physicists. There's a famous story about a judge defining pornography that I think comes to mind here. I don't really know what a fracton is, but if you give me a state of matter, I'll recognize it if it's a fracton. And that sort of comes out of these reviews. Here are some common ingredients. There are theories that have excitations called fractons with the property that single fractons cannot move without prohibitive cost and energy. So at low energy, they're static. They can't move. To move, they must either pair up in dipoles. So in this case, the plus is not allowed to hop, but a plus-minus pair could hop. Or the plus could hop at the cost of creating a new dipole, which, if the fracton phase is gapped, requires an immense energy and so doesn't happen very often. Secondly, in addition to the fractons, or maybe instead of fractons, there can be line-ons or plane-ons, which are particles in a 2- or 3-dimensional theory whose mobility is restricted to lie along preferred lines or planes. So here we see the red guys can move along these axes, the blue guys along these axes, but none of them moves along the whole 2-dimensional plane. They would be called line-ons. And third, just as in the topological field theories like Chern-Simons, there's a ground state degeneracy. But there's a twist. In this case, unlike with quantum Hall, the system size governs the ground state degeneracy. The number of ground states grows with the system size. Now, it's important to say that this is not in the trivial way. Okay? If you take decoupled Ising spins, then the ground state degeneracy grows with the system size. Importantly here, the growth is subextensive, and there should be no local operator that interpolates between distinct ground states. So although the ground state degeneracy grows, the states are somehow importantly distinct. You can't locally move between them in Hilbert space. And related perhaps in an intuitive way to the restricted mobility of fractons, or of these line-ons and plane-ons, these systems can also exhibit glassy behavior or ergodicity breaking. And Vijay could ask me what do I mean by glassy behavior. Thermalization is in some sense very slow, and we could get into what I mean by very slow. OK, so fractons have some features of topological field theory, but they clearly know about the geometry, for instance, the subextensive growth of ground states. And they have some features of systems that localize, for instance, localized excitations and slow thermalization. Now, because this may seem abstract, Let me give a poster child example of a fractonic field theory. And it's going to be very condensed matter. It's taken from the condensed matter literature. Something called the X-cube model. So this is a model defined on a cubic lattice in 3 dimensions, with a qubit living on each of the edges of the lattice. Okay, so here's a cube. On each of the edges, there's a qubit. And we add in the Hamiltonian 2 sets of operators. They're operators that sum over sort of all vertices in the cube and take products of sort of sigma z's, poly sigma z's acting on the qubits coming out in this plane at the vertex. And they do that for all sets of planes. And then there are these B operators that take products of poly sigma x's for the 12 spins on the edge of every cube. Okay, so it's a very simple Hamiltonian. You could have understood it right after you took quantum mechanics. Now, because the various terms in H commute, that's a sort of polyalgebra exercise. I'm not going to do it for you, but it's true. You can minimize the energy easily, and actually in many ways. The claim is that this model exhibits the various features mentioned before. It has fractons. They live at the corners of membranes. If you take the cube, and here I've taken a slice of the cubic lattice, and you act with Z operators along these faces that are parameterized by a membrane, then it turns out there are fracton excitations at the corners. Okay, these cubes that have a single flipped edge have an energy density. They're costly. And these fractons that live at the corners, if you try to move a single fracton, it'll cost extra energy. You'll create more cubes that are frustrated, that have too much energy. So you try to move this guy alone, you can count the number of cubes that you'll create that are unhappy. Okay. But if you move them in a coordinated way, which is a non-local operation, you can do that. It also has line-ons. These look at the ends of connecting strings instead of acting with sigma z's parameterized by a membrane. You act with X operators along a line. The edges, again, have sort of an energetic degree of freedom. And the pairs can sort of move in some way, but the line-ons give you a rigid string. This very simple model also has a big ground state degeneracy. Just counting what you can do to satisfy that all the A and B operators evaluate to -1, which gives a ground state, you'll find that there's 2 to the 2Lx plus Ly plus Lz minus 3 ground states. There are continuum field theory descriptions of this model. First, due to these condensed matter physicists, we will not need them. Now, it is, however, useful to discuss another perspective on it, which will get me, I think, to my attempts to connect to Mike's work in the last 5 minutes. So here's another perspective. There's a famous model due to Kitaev called the toric code. I think the high-energy physicists, it's maybe better known as just Z2 gauge theory. But in any case, here's a way that you can present the toric code that's similar to what I did with X cubed. Here's a square lattice. You again have you have qubits along each edge, and you have A and B operators again. The A operators sum over vertices, right? Products of sigma x's. The B operators sum around a cube, products of sigma z's. And my claim is that this X cube model, whose Hamiltonian was here, and bears a somewhat striking resemblance, at least spiritually, to what's going on in Kitaev's model, can actually be viewed as taking 3 copies of Kitaev's model along 3 sets of planes, right? Along the xy planes, the yz planes, and the xz planes. That would sort of naively give you too many degrees of freedom. There would be 2 of Kitaev's planes going through each edge, and so there would be 2 spins. But if you couple them appropriately, then Ma, Chen, Lake, and Hermele showed that you actually end up with precisely the X-cube model. So the X-cube model is like 3 stacks of Kitaev models coupled in some way by bulk degrees of freedom that couple the 2 qubits on each edge. And that takes us to a subject that I think will bring us soon to a logical stopping point of foliated field theory. So we can view the tiling of the 3D space by sets of planes as a foliation. The presentation of the X-cube model in terms of toric code layers leads us to a more general notion of foliated field theory that is being studied by condensed matter theorists. So let's give an example that leads to a more familiar result very quickly. We'll define a foliation by saying we have a set of 1 forms, E mu, orthogonal to the leaves of foliation. So E of x is a foliation field. Mu runs over the different foliations. Here's an example of a foliated gauge theory. It will be pretty trivial, but it gives you the idea. We can define a foliated U1 gauge theory in terms of a two-form. So let's take a two-form B that satisfies B wedge the foliation field as 0 and satisfies a gauge principle. You can add to B D of any one form as long as lambda is appropriately orthogonal to the foliation. And here's the Lagrangian dB wedge star dB. Well, if we just, let's get an idea for what this contains. Let's take the simplest possible E, which is just dz. So we have a foliation by planes going up along the z-axis. We can locally solve our equations by saying B is some B tilde wedge dz, so that B wedge E is 0, where B tilde has a sort of dt, dx, and dy components. We can satisfy our constraint on the gauge parameter to turn it into a scalar function by saying, since lambda wedge E is 0, lambda should be lambda tilde dz. What is the resulting theory? It's not quite a conventional gauge theory. What it is a gauge theory in 3+1 dimensions that has a sum of Maxwell terms on 2+1 dimensional planes, but nothing in the z direction. It just summed over the z direction, okay, like this. And the way that I would describe this to a string theorist, and then I'll fix my description, is that it's pretty clearly like a stack of D2 branes spaced along the z-axis into a string theory up to the normal problem that string theory adds a bunch of supersymmetry and fermions. Now that's not quite right. In string theory, we'd worry about the W bosons, right? If you have these D2 branes, there are W bosons, and they make the action look more complicated than this. They don't decouple from one another. So to get an array of L nicely coupled D-branes, you need to take a sort of new scaling limit of parameters, okay? Which would be, you take the spacing between these objects to 0, as in the foliation, and you take L string to 0, or you take the string mass to be very, very large. But instead of keeping the W mass fixed, which is normal in brane engineering of gauge theories, you do things so that the W mass actually stays very large. Okay, and then you keep G finite, and I'll fix this statement in a second. Okay, so in that limit, what you'd think you'd find is something like an action that looks like this sum over decoupled copies on 3-dimensional slices plus superpartners summed over a 4th dimension. Now that's not quite right. To really get a continuum foliated field theory, and not this sum, you want to factor out a delta as in a Riemann sum and rewrite this as an integral dz in a limit where delta is going to 0 and the number of copies is going to infinity along the 4th direction. And so you get a new foliated coupling, which is g Yang-Mel squared times delta. And you take the limit holding this g foliation fixed instead of g Yang-Mels. Okay, so this is a new thing you could do with D-branes. It's, in this particular case, not very interesting, right? What you get in this case is a bunch of decoupled stacks. I don't think we want technology to describe a bunch of decoupled stacks. Okay. But the important point is that a wide variety of less trivial theories of what are called type 1 fracton orders are thought to admit a description as these foliated field theories. And the coupling of foliation fields to simple bulk dynamics, which then talks between the different leaves of the foliation, is what produces non-trivial phases. And that was studied starting with these papers, and then by the group at Station Q more mathematically. So the example with D2s is a bit too trivial. I'll discuss one non-trivial example, and then I'll close. So we can easily do better using, for instance, intersecting branes. Okay, and here I'm morally generalizing. Instead of line-ons that are gapped matter, I'm taking conformal field theories. And Mike's work on branes intersecting other branes, Mike's work on branes within branes, all of that in these kinds of sort of tinker-toy constructions is absolutely crucial. Okay, but anyway, here's a simple configuration where we can do this. You could take a D3 brane as the base 3+1 dimensional space, and you could get the leaves of the foliation by intersecting it with stacks of D5s on 2+1 dimensional planes, the XY planes. So that morally gives this stack of planes immersed in a 3+1 dimensional gauge theory. Each plane has supersymmetric QED dynamics because there's a bulk QED field on the 3 brane, and there are hypermultiplets localized on the planes, and they're coupled by 3+1 dimensional bulk gauge dynamics. Okay, this is a sort of brane analog of the kind of things that come out of stacks of toric code. This is a theory that has obvious planons. There are analogs with further intersections that give examples with fully localized fractons. I will not have time to discuss them. Okay? And the one thing I'll try to convey about these here, because I'm out of time, is that one thing these theories bring you is interesting new dualities. Okay? So to see this, you could just strip away the supersymmetry and consider the case with charged scalars on these planes coupled to bulk QED. And adding the supersymmetry will lead to a cousin of this duality that I'll just state at the end. Okay. So what is the action like? Well, there's an action for the planes and an action for the bulk. The bulk action has a gauge field with theta parameter. The action on each leaf has a charged scalar. Here, since I have no supersymmetry, I've written it in nonlinear form as if we've Higgs the U1. Okay, I could promote that to a linear form by complexifying the scalar. So here's the kind of action you'd get on the planes. And you can sort of derive new dualities by considering combined actions of sort of well-known dualities of these systems. So one thing you could do is you could take bosons on these layers, and you could dualize each to an abelian gauge field using the inverse of the transformation I started with when discussing mirror symmetry. So you could take this action and replace the sigmas, the scalars, with gauge fields little a along each plane coupled to the bulk gauge field by a K matrix or by Chern-Simons terms.